Good afternoon, ladies and gentlemen. In this short video, I'm going to go through the problems to prepare for practice A in chapter 16. Before I do, I want to draw your attention to this handout that I posted in Google Classroom, and it's actually for chapters 16, 17, and 18, and it's double-sided. The backside's mostly chapter 18. Okay, so I want to draw your attention to the top part of it. Make sure you take a look at that, and I really do hope you will read the chapter to help you understand. We need to understand electrical charge and electrostatic, and like when you rub a balloon on your hair. By the way, that's why I gave you guys those balloons, is for this part. So given two charges of magnitude Q1 and Q2, so we actually have units for electrical charge, and the units are coulombs, and they're separated by a distance. So here's Q1 and Q2, and there's distance D between them. Magnitude of the force that each of them is experiencing due to the other is calculating using Coulomb's law. Now, maybe you remember that positive and negative attract, positive and positive repel, negative and negative repel. And there is going to be an extra credit lab where you can work on a real simple worksheet, and there's a video to follow along with it with strips of foil paper and so on. So you can experience the attraction and the repelling. So here's our equation. We have a constant. It's called the Coulomb constant. And this one I don't have memorized because I haven't used it that much. 8.99 times 10 to the 9th. And notice the units, Newton meter squared divided by Coulomb squared. So that is our K sub E for the electric force. We're talking about electrostatic force. And then the units of the Q1 and the Q2 charges divided by the square of the distance between them. Okay, oh, here's the Coulomb's constant as well. All right, so let's take a look at the preparation problems. And it's on page 581. 581, we'll start with the first one, my pen. Okay, the first one, at a point of fission, a nucleus of uranium, atomic number 235, that has 92 protons is divided into two smaller spheres, each of which has 46 protons. 46 plus 46 is 92. And a radius of 5.9 times 10 to the negative 15th meters. What's the magnitude of the repulsive force pushing these two spheres apart? Why would they be pushing apart? They're both protons. So we have positive and positive, and they are going to repel. All right, so here's what I wrote down for us for this problem. I've got uranium, 92 protons, and it says it's separated into two spheres. Each of them have 46 protons. And they say the radius, now they're talking about the radius of each of the protons, is 5.9 times 10 to the negative 15 meters. So here's our equation. Here's our equation. The Coulomb constant, which I wrote for us here, 8.99 times 10 to the 9th, times the charge of one times the charge of another, divided by the distance between them. So what are we going to do for the distance between them? They didn't give us that. They just said the radius, looking for my other pen, the radius of each of the protons. So I drew these two. Picture this is going to be one proton. This is another proton. It's closest they can be together. So you'll notice here's the radius of this proton. Here's the radius of this proton. So the closest distance between them would be between this center and this center has to be 2 radius. So for here, we're going to do 2 times this radius. Okay, so that's going to be 2 times 5.90 times 10 to the negative 15 meters. Okay, so that's what we're going to do for the radius, the distance between them. All right, the next thing is, where's the charge? They didn't tell us how much the charge is. Well, you got to look in your book. It's page 560. On page 560, you see the page number 560? There it is. So they have figured out the charge and mass of electrons, protons, and neutrons. So here it is. For the electron, you figured it was negative, and negatively charged, net negative charge, negative 1.60 times 10 to the negative 19 coulombs. And notice it's the same magnitude for the proton, but it's positive. But the magnitude is the same, 1.6 times 10 to the negative 19 coulombs. Interestingly enough, though, the mass is not the same. In fact, a proton mass is way, way, way more way more than the electron. How do I know there's fewer zeros in front of these numbers? Because the proton has a lot more mass than the electron. Neutron, here's the mass, but there's no charge because it's neutral. There's no net charge. Okay, so this is the number that I want, negative 1.60 times 10 to the negative 19. That book here. So I know that the Q of a proton is plus 1.60 times 10 to the negative 19 coulombs. There we go. All right, but the thing is, we have more than one. In fact, this whole thing, there's 46 of them, and this one's 46 of them. So this Q1 is going to have to be 46 of these, and this Q2 is going to have to be 46 of these as well. So let's rewrite this equation and put it down here towards the left here. Here we go. So the electric force here is going to be, the first is the K, which is 8.99 times 10 to the 9th. And I'm going to go ahead and do the units so we can see that the units should cancel out. Coulomb squared. There's my constant. Now I need the Q1. Well, the first one is 46 of these guys. So I'm going to have to say here, make it longer, times 46 times this Q, 1.60 times 10 to the negative 19 coulombs. And then the other one, which is also 46 times 1.60 times 10 to the negative 19 coulombs. There's our numerator. Oh, I noticed right away that I've got a coulomb here and a coulomb here, and I have Coulomb squared. So that gets rid of these coulombs. All right, now I'm still missing the R squared. So I'm going to put this in brackets. 2 times 5.90 times 10 to the negative 15 meters. And that's got to be squared. Remember, in the denominator, squared. I draw your attention to this equation here before we go on. And maybe you remember gravitational force. Do you remember we did gravitational force? Gravitational force. And that one was a constant G, big G, M1, M2, all over R squared. The same concept here. And plus it looks similar. So the distance between the two masses squared, and then we use masses and then the constant G. So notice a similar format here where we have a constant times the charges of each one divided by the distance squared. So there we go. This one here is the Coulomb's law. All right, so you're going to notice that these problems are pretty straightforward, pretty easy. It's just plugging them in. This is where you're going to get really good at using your calculator, right? Or you should get really good if you aren't already. But I want to go back to units. I see here meter squared. Well, this meters here is going to get squared, so my meter squares cancel out. And that can be it. Meter squared. And I'm left with newtons, which I would expect because that's the units of force. All right, so now we get the fun with the calculator. Move it up here so you can see. Maybe I'm going to have to unzoom a little bit. There we go. All right, so I'm going to start with the numerator. I'm going to start with the numerator because I like to be cautious. I'm going to go 8, I'm going to put parentheses just in case. 8.99 times 10 to the 9th. And then somebody taught me, close the parentheses. All right, that's the first part. Now I notice that there's two 46s. There's a 46 and a 46. So why don't I rewrite this? I'm going to make it easier for myself. So I don't have to type in so many. I'm going to say this is actually 8.99 times 10 to the 9th. And I'm already done with units. I end up with newtons here. All right, and I got 46 times 46. So that's 46 squared. And then I have this number, 1.6 times 10 to the 19 times itself. So that also times 1.60 times 10 to the negative 19 squared. And all that divided by, same thing, 2 times 5.90 times 10 to the negative 15 squared. All right, so I got the first one in, and I'm going to put the 46 squared. So times 46 squared. There we go. Okay, times, now I'm going to use the parentheses. Make sure that I get this all, just that part. And what is it? 1.6 times 10 to the negative 19. 19, bring down to parentheses, and that I need to square. All right, so there's my numerator. I'm going to go ahead and just say, give it to me. All right, so I'll write down just the numerator, just in case I need it, mess up somehow. 4.86984, blah, 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 times 10 to the negative 25. Okay, that's my numerator. Now I'm ready to divide it by the square of this business here. So I'm going to say divided by, and I'm going to use parentheses again. I want that whole thing in the denominator to be squared. So I have less space here than I want. Okay, try again. So you can see that. So I got 2 times, I can't see what I'm doing, 5.90. Nope, that came out 5.91. Try again. 5.90 times 10 to the negative 15. There we go. Bring down the cursor. There's my parentheses, and I need to square it. All right, so now I'm ready to say, please square that. Divide it to what we had the numerator. And there it is, 3,497. That's a lot of force, huh? So I have the force here is 3,497.448 newtons. So we can say that's about 3,500, if we only needed 2 significant figures, 3,500 newtons. I know some of you guys really like scientific notation, so of course that would be 3.5 times 10 to the 3 newtons. Okay, 3.5 kilonewtons. But this is fine, 3,500 newtons. So all we did was we applied the Coulomb's law, but because there were 46 of the charges, we had to take that into account. So one little ball was 46 of it, the other ball was 46 of it, and we end up that those 2 balls have experiencing 3,500 newtons. Okay, so one from the other, and they're repelling each other. So you can't say positive or negative. If you did, you'd have to say, well, this one's going to the left, this one's going to the right. So we just say repelling. Okay, so this would be repelling, a repelling force. All right. Okay, so let's look at the next one. Next one's right here. Right here, and I think I'm gonna flip the book around. I'm gonna take as much space. Okay, the next one, number 16. What is the electrical force between a glass ball that has 0.25 microcoulombs? You can see that. Microcoulombs of charge, and a rubber ball of negative 5.0 microcoulombs of charge when they're separated by a distance of 5 centimeters. So right away I notice, okay, one's positive, one's negative, so they're going to want to attract. They're going to attract each other. That'll be an attracting force instead of a repelling force. All right, so let's write that down. Let's see, let me turn this page. So, okay, here we go. So what do we have? We have that the first one, I'm going to call that Q1. Q1 is negative 2.5 microcoulombs. And the other one, Q2, is positive 5.0 microcoulombs. And they have a distance, so that's the R. R is 5 centimeters. So hopefully you're like, centimeters, what should I convert that? Well, let's look at our equation. Our equation is the K times Q1, Q2 all over R squared. Okay, so K is 8.99, what is it, times 10 to the 9th. I don't have this one memorized. Newtons meters squared all over Coulomb squared. Oh, it's meters squared. So if I want factors here canceling out, then I better be using the same units. So this centimeter is not okay. It has to be in meters. Okay, so 100, there's 100 centimeters in 1 meter. So I'm going to divide this by 100. So R is equal to 0.05 meters. Okay, that takes care of this part right here. All right, now this one's microcoulombs. So we need to have it in coulombs, not microcoulombs. So what's a micro? Remind you, 1 micro anything, micrometer, microcoulomb. 1 micro is the same thing as a millionth. millionths. So 0.00005 zeros and a 1. Okay, so we're going to change this to coulombs. This is just going to be 2.5 times 10 to the negative 6, and this would be 5.0 times 10 to the negative 6. All right, so let's do that. So there's my K. Let's do the Q1. Q1 is 2.5. I won't worry about the sign. 2.5 times 10 to the negative 6. All right, coulombs. Oh, let me extend my numerator. Coulombs, and then the other one is times 5.0 times 10 to the negative 6 coulombs. Okay, so my coulombs cancel out. Here's coulombs, cancels out. Coulomb here and coulomb there. And I need my R. Here's my R, 0.05. So that, sure that times 0.05 meters, but I need to square it. Remember, you need to square it. Highlight it or something. Remember, make yourself, you need to square it. Okay, and then my meter squared is going to cancel out with this meter squared. This meter squared cancels out with that meter squared. So then I end up with newtons again. All right, so ready for the calculator? Here we go. All right, let's get I'm just going to do the numerator first. So I've got 8. They're all multiplication, so it doesn't matter what order I do them all. 8 times 10 to, nope, 8.99 times 10 to the 9th. There we go. That's my K. Let's do the next one, 2.5 microcoulombs times 2.5 times 10 to the, caramba. All right, so I forgot to bring it down. Oh, good. 8.99 times 10 to the 9th. There we go. Caramba. All right, here we go again. 8.99. See, still takes practice using your calculator. Times 10 to the 9th. There we go. And I have to bring down the cursor. Times 2.5 times 10 to the negative 6. There's my microcoulombs. Bring down the cursor. Times 5 times 10 to the negative 6. Bring down the cursor. All right, there's my numerator. I'm done. There's my numerator. Okay, there's my numerator. Now I'm going to say divide that by, and I'm going to put this in parentheses though, 0.05 meters, and that I want squared. Maybe I didn't need parentheses, but I always say there, so sorry. There we go. And I get 44 equals 44.95 newtons. So with the significant figures that they gave us, just 2, that would be about 45 newtons. There we go, 45 newtons. So all we did was we applied the same equation, which is Coulomb's law, using Coulomb Constant. But we just had to make sure we were careful with our units. So distance has to be in meters, or the radius they call it. And we need coulombs, not microcoulombs. Okay. So let's do the last one, which I believe is on the next page or next column. I don't remember. Here it is. Oh, maybe I can do it on this page here. All right, an alpha particle. Oh, look at that. Charge is 2 times E. So we're like, what is E again? E is what we found on that table. Here's E. The charge of E is just going to be negative 1.60 times 10 to the 19. So this one here is 2 times that. So let me write that down. The charge Q of an electron is, this one's going to be negative 1.60 times 10 to the negative 19C. Okay, so that's what E is. So an alpha particle is twice of that, is sent at a high speed towards a gold nucleus, and its charge is 79 times E. What is the electric force acting on the alpha particle when the alpha particle is a certain amount of distance from the gold nucleus? All right, so our Q1, I'm going to write this down. Our Q1 is going to be plus 2 times this guy right here, the negative 1.60 times 10 to the negative 19 coulombs. That's our first one. The next one, we got 79 of them. So Q2 is going to be 79 of the 1.60 10 to the negative 19 coulombs. Okay, so what is the force? Now remember, we're not caring about the sign. It's either going to be repelling or it's going to be attracting. Okay, so that's why I'm not going to worry about the sides. All right, and then we have a distance. That's our radius. So our radius is 2 times 10 to the negative 14 meters. There we go. All right, we write down our equation. What is it? I gotta go on this side. On this side, here we go. The force there is our constant, our Coulomb constant, times Q1 times Q2 all over the distance squared. So I'm going to go ahead and just start plugging that in. First, I need that constant, which still is 8.99. I still don't have it memorized, times 10 to the 9th. Newton meters all over Coulomb squared. Now, I like putting units just because it keeps me accountable. Make sure that I don't forget somebody. All right, so there's that one there. So the next one's going to be 2 times 1.60 times 10 to the negative 19 coulombs. And the next one is 79 times 1.60 times 10 to the negative 19 coulombs. Okay, my coulombs go away. I have 2 Coulomb times Coulomb in the numerator and a Coulomb squared in the denominator. And down in the bottom, put in parentheses, 2 times 10 to the negative 14 meters squared. And then my meters are going to cancel out. This was supposed to be meter squared, no? Yeah, this was supposed to be meter squared. Notice I noticed that because it didn't cancel out. So a meter squared and a meter squared cancel out. Okay, so I notice that these two factors, the 1.60, are the same. So I'm just going to write it once and square it. Okay, so if you want me to rewrite that, I can. I'm just going to take these two. These two are the same term. Same terms. So I'll just take that and square it. Okay, let's start with that first. You can see that I'm doing that. Okay, move this up so you can see that. All right, clear. So I'm going to start with, I guess I'll put in parentheses, 1.6 times 10 to the negative 19. I have to look at it. Negative 19. Bring it down. Okay, my controls here are in the way. I need to move this thing. I can't see. Okay, there we go. And then close the parentheses. And I want to square that. That's the first thing I'm going to do. I'm going to take care of these yellow ones. Please square that. Okay, good. I squared it. Now I can continue. Let's see. Times, we'll do this other one, then times 2 times 79. We'll do this other big one. I'm going to put in parentheses. 8.99 times 10 to the 9th. I think. Bring it down. There we go. Okay. Times 2 times 79. Okay, boom. All right, there's my numerator. Big, big numerator. Okay, now I'm going to say divided by. Please do not write this down and start rounding things off because then you're introducing error. Never round off until the very, very end of the problem. All right, let's divide that by, and I'm going to put in parentheses because I got to square this thing. 2 times 10 to the negative 14. 2 times 10 to the negative 14. Bring down my cursor, close parentheses, and please square that. And there we go. There we go. And I get a small number. It looks like I made a mistake somewhere. All right, so you guys got to check where did I make a mistake. I'm going to try this again. Did I not multiply something? Probably. Or I typed something in wrong. I'm going to take it again. I'm going to clear it out and do it again because this is so important. I make mistakes and I realize that I wrote something down incorrectly and that's why it's wrong. Okay, so I'm going to try again. By example, you can see what I mean by making sure you're using your calculator right. 1.6 times 10 to the, make sure I'm writing this down, negative 19. Negative 19, there we go. Bring that, close the parentheses and square it. All right, times. Let's see, I'm going to go ahead and do that times the 2 times the 79 because I can't see what the other one is, times, because it's covered up by the controls on the screen, 8.99 times 10 to the 9. Bring down the cursor. Hopefully I did this one right. Okay, and I get a big number, the numerator, and write down the numerator on this one. Now let's see, if I get that right, I'm going to divide this by, and I want to square 2 times 10 to the negative 14. Negative 14. I want to bring down the parentheses. Hope I got that right. Am I missing anything? And I got to square that guy. Square that guy. There we go. All right, this time I did it right. So you got to really be careful. Maybe you'll roll back and see where I typed the wrong number somewhere, but this is correct, 90.9. So as you guys have noticed, I always say check your work. If you have time, check it again. Make sure you got the right number. So I got 90.90688 newtons. So with two significant figures, that's about 91 newtons. All right. So there you all have it. It's just using the Coulomb's law. That's all we're doing in this set of exercises, this homework. And you've got to use the Coulomb constant, which is 8.99 times 10 to the negative, 10 to the positive 9 newtons meters squared and divided by Coulomb squared. So that's all I have. I'll see you guys next time.